the chat is quiet. So I think we can probably pass on to Patrick. So Patrick Kidger is from Oxford. He's going to talk to us today about universal approximation transposed. So yes, thank you, Patrick.
Right, hello, I think, can you hear me now?
Yeah.
Okay, and hopefully you can also see my screen. Okay, so hello everyone, thank you for the opportunity to speak. And as the title suggests, I'm going to be talking a little bit about universal approximation. What am I going to be discussing today? I'm going to start off with a brief discussion of classical universal approximation. And in particular, this is actually going to tie back to some of what we heard Gitta talk about earlier, where she actually briefly mentioned the classical universal approximation theorem. And then I'm going to move on to discuss what I mean by transposed universal approximation. This sort of, I don't want to say it's a new way of doing universal approximation, but it's another take on it. So I'll try and tell you about what the main result is and just some intuition for how it comes together. And then I'll try and tell you a little bit about the applications of this. Essentially, why should one care? Why is this a theorem that was worth proving? Then I'll move on to some extensions, and then those will motivate some open questions because there's quite a lot that we still don't know. Okay, so first of all, classical universal approximation theorem. So let's start off with the informal picture, or as I was once told in undergraduate, proof by dodgy diagram. And so for this particular version here, the idea is you have this single hidden layer neural network. You've got some number of nodes in the input layer, this one hidden layer, which we will allow ourselves to take arbitrarily wide, and then this one single output neuron. And then the classical theorem, informally put, states these sorts of wide, shallow networks with a non-polynomial activation can approximate any function. And then once again, sort of as Gitta alluded to, this is one of these foundational results on why neural networks work. It says that it doesn't matter what you're doing. In principle, a neural network can do the job. It can approximate whatever it is you're trying to do. Okay, so that's the informal version. The formal version, this is going to be a slight adaptation of what we saw, is that we have some continuous function, and then we're going to consider the class of neural networks which have this as an activation function with some n neurons in the input layer, one neuron in the output layer, and then this one hidden layer with an arbitrary number of neurons. This is this picture I've just shown. And then we can say that on some subset, our neural networks are dense in the continuous functions if and only if rho is non-polynomial. We can approximate any function if and only if rho is non-polynomial. So in particular, we have both sufficient and necessary conditions here. Okay, so hopefully that's reasonably straightforward. That's the classical version. I'll put the picture back up again. But of course, this isn't really what we do, right? In machine learning, we don't have one hidden layer. I'm sure we have at least two in modern machine learning worlds, maybe even three. And does the classical theorem apply here? Well, actually, yes, it does. It is quite straightforward to see this. In principle, you can ask that you can just apply the classical theorem to the first hidden layer, ask that approximate your desired function, and then have your second and third and so on hidden layers just approximate the identity, which they can do by the theorem, right? The identity is one of these functions that we can approximate. So it's actually quite clear that for any such network, which is bounded depth and arbitrary width, that the classical theorem applies. Okay, and I refer to these as shallow wide networks. Now, when I look at this picture, I think there's a sort of natural question which comes to mind. And I think the title of my talk rather gives it away for what that question is. And it's to say, oh, what if we take this picture and just kind of turn all those blue dots in the middle on their side? So this is what I call a deep, narrow network. And then in particular, we're also going to explicitly consider the case of having multiple output neurons. So you can see I'm just adding them at the top there. Because if you recall back to this shallow case, right? If we had multiple output neurons, then well, this is easy to do. You just have some arbitrarily wide network doing one output neuron and another arbitrarily wide network doing the next one, and you put them all together, and the whole thing is still arbitrarily wide. But in this regime, we have some bounded width. We have some budget for how wide we can go, so we can't repeat the same trick. So we need to explicitly consider multiple neurons, output neurons, all at the same time. Okay, and then the question is, can we get universal approximation? And judging from the fact that I'm sitting here talking to you now, you've probably guessed that the answer is yes. Okay, so when I say, can we get universal approximation, I think we need to qualify that slightly. What are the questions that we're really trying to answer here? Because for starters, what activation functions work? In the classical case, we required that the activation function be non-polynomial. And in fact, this was both necessary and sufficient. Is the same going to be true here? The answer is no. We will see that things are actually quite different in this case. How narrow can the network be? Because it's quite clear that if your network is too narrow, then you're not going to get universal approximation. An easy way to see this is that if at any point your network width goes below the number of input neurons, then what you end up doing in making that sort of linear map from input neurons to something with lower dimension is that you're making a linear map from a high dimensional space to a low dimensional space. So it must have invariant lines, invariant hyperplanes in general. So clearly there is some minimum width below which we cannot go. And then also, when we say universal approximation, when we say density, what notion of closeness, what topology are we using here? So this can be things like the uniform topology, Sobolev topologies, LP topologies, and so on. Okay. And I'm now going to introduce one definition. I promise this is the only piece of notation that I'm going to introduce in my talk. So hopefully it'll be quite reasonably clear to follow along. This one piece of notation is that we're going to consider these neural networks, in particular these deep, narrow neural networks with n input neurons, m output neurons, k neurons in each hidden layer, and then as many of these hidden layers as we like, and then activation function rho. So I think maybe it's helpful if I just go back to this little picture that we saw earlier. So here we have n equals 4 inputs, m equals 3 outputs, and our width k equals 5. Okay, so that's our definition. And then the main result that we've got is to say that if we now have any non-affine continuous function, which is continuously differentiable at least one point with non-zero derivative at that point, so that's a technical condition, which I will try and discuss in a little bit more detail in a moment. But for now, this is just, I want you to appreciate this is an incredibly weak condition, right? We're just saying that it's basically just saying that at some point we're differentiable with non-zero gradient. And so any activation function you might practically imagine using will actually satisfy this condition. And then we're going to have much the same story as before. We're going to have this complex subset, and then we're going to find that our deep feed-forward neural networks, narrow feed-forward networks, are in fact dense in the continuous function. So we can in fact get universal approximation. And so in particular at this point, actually no, so before I get onto that, this is the informal statement, right? That we can approximate anything with a deep narrow network. And so in particular, I'd invite you to think back to those possible questions that I posed earlier. So what topology? Well, here's the uniform topology. And so of course, in particular, this implies things like the LP topology on the compact sets. Then the width, I've given this explicitly as n plus m plus 2. So, and of course, this also, if you have any wider network, then that's just a special case. You can just ignore your extra neurons. So we can handle those two. And then the activation function is nearly any activation function. And in particular, this is a point I will emphasize later, it includes polynomial activation functions. So this is this genuine difference between this case and the classical case. Okay. And there's one particular trick which I'm gonna be using to get this working. And this is that technical condition on the activation function that we introduced. So I'll state that again, continuously differentiable at least one point with non-zero derivative at that point. So what that's saying, right, is that we have this point in our activation function where we can zoom in on it, and it's going to look like a non-zero straight line. That's what differentiability means, is that locally you look like a straight line. And in particular, we're just asking that this should be a non-zero straight line, linear or affine, depending on your terminology. And so what this then means, this is really crucial, is that the composition of a linear function and an activation function and a linear function can approximate the identity. Because we can use our first linear function to do that, zooming it in all the way. Then we move to our activation function, which is now just on this zoomed in region, is now locally approximately linear. And then we can use our second linear function to adjust the gradient, because we have non-zero derivatives, so we can in fact make this change. We can adjust the gradient, and then we can zoom back out again. And thus we get some approximation to the identity, which is again a linear straight line. Okay, and the reason this is so important is that we're in this width-bounded regime. So at each layer, we can only do a very limited amount of computation. And in general, what we're going to have to do is remember things in memory between layers using these approximate identities until we're ready to compute them. Okay, so I'll try and give a sketch proof of why this is true. I realize that the point at which the speaker starts talking about their results in technical detail is the point at which everyone switches off. So I'm going to try and keep this reasonably sort of informal and stick to the pictures rather than the mathematics. So as you see, we've got our 2 input neurons at the bottom, and here for simplicity, we have just 1 output neuron. And what we're going to do is we're going to use these dots to represent scalar values in the way that you've probably seen in 100 neural network pictures by now. And then we're going to join up the dots with arrows, representing this linear and activation function together. So then what we're going to do is we're going to copy our inputs into some of these hidden neurons, just using the identity function, which is that trick that I've just described. That the activation function can be made to be the identity approximately if we wanted to. And then we're just going to repeat that all the way forward. And so at this point, what this means is that we have now remembered our inputs at every single layer throughout our network, approximately up to some approximation of the identity. So what this means is that we can now always query that. We can now always understand where we're trying to evaluate our function. And what this now means is that we can now perform some small arbitrary amount of computation. So we do some small amount of computation based off our inputs. And then what we can do is we can just add those together. So the reason we can do this addition is, of course, we have this linear transformation in between. So that in particular allows us to add things together. And then essentially the same thing as before, this identity trick I've described means that we don't need to worry about our activation function messing things up. And then basically what we're going to do is the same thing as we go through layer by layer. We do a small amount of computation. We add things up, a bit more, add things up. And then finally, when we get to the end, we're just going to copy that to the output. And so what we're doing here, this idea that you can approximate your arbitrary function just by adding up lots and lots and lots of little bits of all of computation that have all been done. This is actually exactly the same intuition as applies for the classical universal approximation theorem. If you cast your mind back to that picture I presented earlier, we had this shallow network where you had this one single hidden layer that was incredibly wide. And so in that context, each neuron in the shallow case, in this shallow and wide case, each neuron is doing some small amount of computation from the inputs, and then the output neuron adds them all up. The output neuron adds up all the hidden neurons. And we're doing exactly the same thing here. And in fact, it's actually in the if you have a non-polynomial activation function, you can actually prove this via the classical theorem. You essentially just take the classical theorem, just sort of turn it sideways. So that's kind of neat. I think another very important comparison here is to computer programs. And in particular, what I mean by this is these sorts of like register models where you have operations between them. If you've ever tried to write down computer programs where you're really trying to keep track of exactly what's in memory, then something you may well have done is have these straight lines going across your page representing a register where you're storing information, and then lines moving between them representing operations between the registers. And this is essentially exactly what's going on here. We have 2 input registers over on the left-hand side and 1 output register on the right-hand side. And then in between, we're performing some small amount of computation and transferring results from one register to another, performing operations between registers. So this is really analogous to the memory-bounded regime of computer programming. Okay, next up, sparsity. This network is very sparse. And so I think that's just sort of kind of interesting. But in particular, if you're interested in trying to measure the complexity of this, then sparsity is one such measure of complexity. This was Gitter's chosen measure of complexity as well. So we can see that in some sense, this is efficient in some sense. Next up, constructive. I'm not going to spend too long on this, but all of our constructions, obviously this is just a sketch proof, but the actual proof is constructive. We can, in principle, write down the neural networks that are going to do the job. And then something I've also touched on briefly is that polynomial and non-polynomial activation functions, we actually have to prove separately, because a non-polynomial one is super easy to prove. It's just the classical case, turn it sideways. But for the polynomial one, then this is sort of, you have to go back to scratch. You have start from scratch. And so in particular, the way things work for this one is that you're going to try and approximate any polynomial. Okay, that seems plausible. Stone via Strass, good way to go. And in particular, to get the width down, there's actually another trick we invoke where we can approximate the reciprocal function in a width-efficient manner, which I think is kind of cool, but I don't think I'm going to spend too much time on here. Okay, so that's the sketch proof. Quick comparison between shallow and deep networks between what I've been describing. So the shallow case, this is the classical case, arbitrary width, bounded depth, non-polynomial is necessary and sufficient. And then this is what I've been describing here, bounded width, arbitrary depth, and almost any activation function. And then the point I really want to emphasize at this point is that we have this qualitative difference with respect to polynomial activation functions. It's kind of a hot topic as to what's the benefit of depth in a neural network? What are we gaining from it? And in some sense, this is a qualitative difference that we are gaining from it. Bounded depth networks do not exhibit universal approximation with polynomial activation functions. Arbitrary depth networks do. Okay, so applications. Obviously, this is a mathematical theorem, so I'm not going to pretend that it's going to solve real-world problems just yet, but it can hopefully help out. And so, in particular, if one is proposing a new model, then it's often nice, it's not necessary, but it's nice to demonstrate universal approximation to show that your chosen model can, in principle, learn whatever it is tasked to do. And this is really giving a new way to do that. And so in particular, I actually know of a few papers which have used this to go and demonstrate universal approximation of whatever their chosen model is. Next up, an understanding of bottlenecks. If you're familiar with autoencoders, obviously those are a little bit out of fashion these days. But if you think of an autoencoder structure where you have a bottleneck, you want to introduce a bottleneck to learn low-dimensional representations of your data. Then what this theorem is saying is that if your bottleneck is of width greater than or equal to n plus m plus 2, then it's not a bottleneck. And so this is giving some theoretical understanding of what's going on with those. Okay, so those are the slightly more practical end of the applications. The slightly more theoretical end of applications is that we handle much broader classes of neural networks. We can prove universal approximation for much broader classes of neural networks with what I've just been describing, because I've been presenting it as this sort of width-depth dichotomy. But actually, if you are willing to consider slightly more complicated classes of neural networks, where maybe width and depth increase simultaneously, and you can't choose to just have one or the other, then actually the classical theorem doesn't apply to such classes of networks, because in principle, as you go up through the layers, then things could be getting more and more muddled faster than your layers can be approximating the identity to set things straight again. So the classical theorem doesn't apply there, but here this is clearly a special case of what we're doing here, because if we're increasing in width and depth simultaneously, then we can just ignore the extra width and pretend we're only increasing in depth, and our theorem applies. And then, as I've already mentioned, we have this nice difference between shallow and deep. Okay, so what about some extensions to what I've just been describing? So if you recall, the main result had this width of n plus m plus 2. It's actually possible to show for most activation functions that you can have just n plus m plus 1. And this plus 2 is really just like a technical detail that arises in one special case. So I think it's probably quite natural to wonder, can this be improved? Another one is non-differentiable activation functions. If you recall, we had this technical condition on the derivative, but it's actually possible to show that for certain non-differentiable activation functions, you can pull more or less the same trick, that if you have a very nice activation function, you can get it to look like the identity, even if it's non-differentiable. So we can show that for certain non-differentiable activations. And then also, as another result, so this is the only time I think that I'm going to be considering the value in particular. But for the value in particular, we can show universal approximation in LP on Rn. And so the point I want to emphasize here isn't actually the LP topology, but it's the fact that we have a non-compact domain Rn. I think that's really the interesting bit here. And as you might recall, the main result was continuous functions on a compact domain. Okay, and as I said, I think these motivate some open questions. Where can one go from here? What's the size of the network? So in principle, these proofs are constructive, but how big does these networks actually need to get? It's slightly dubious, I think, actually, to whether or not this is necessarily an interesting question in this regime, but I probably won't have time to discuss that further. Another one is the width. Can it be reduced further? Because, for example, it is known that for the particular case of the value, which has been incredibly heavily studied theoretically, that you can do slightly better. We can drop down to just n plus m, and it's possible to prove that, at least in the m equals 1 case, that this is optimal. And so that's in terms of upper bounds. What about the precise minimum width? What I'm really meaning here is what about lower bounds? But because I mentioned earlier, by this sort of like I discussed invariant hyperplanes, that if you go too narrow, then you can't get universal approximation. And that's saying if you go down to n minus 1. But actually, it's possible to show via a rather more subtle topological argument that n is too small. What about general non-differentiable activations? I've only considered this one special class. Can we get density in LP var n for non-value activations? And then also, can we consider other topologies, in particular maybe Sobolev topologies? And there has been a variety of work on Sobolev topologies, but none as far as I know for the deep and narrow case. Okay, so with that, I'm pretty much done. So this is the paper that I've really been discussing today, universal approximation with deep narrow networks. This is some of the significant previous work on the deep and narrow case. Most of it just specific to the value. That's really what we were sort of innovating on, was handling arbitrary activations. And then this is the classical case for the shallow and wide. And with that, I think I'm done. So thank you very much for your attention, and I'll take any questions.
Thank you very much, Patrick. It's a very interesting talk. Yes, please put any, oh, Stephen Watson has a question. Let's see if I can unmute him.
Yeah, can you hear me?
Yes, I can hear you.
Yeah, super. Oh, fantastic talk. Love that.
Thank you.
You touched on the Sobolev space part at the end, and that was kind of the direction of my question. So you had this trick, which was the C1 trick, so continuously differentiable. And I was kind of wondering, what's the weakened version of that? Are there Sobolev space versions of that? And related is the question of, if you're thinking of optimization over choice of this row function, are there questions about how one best selects a row? So
okay.
Spaces and their completeness help in that regard.
In terms of, one at a time. In terms of Sobolev spaces, I've got to be honest, I know very little about what this would look like in Sobolev cases. I've not thought about it specifically. So I'm afraid I don't have much to add there.
Don't be afraid of that. It's just a thought.
My intuition is that if you want to sort of mimic what we've already got, is that you'd need some sort of higher derivative condition. Then we have this sort of first differentiable. Maybe you need second differentiable or something like that.
Maybe you do something like this,
yeah, maybe it's something like that. In terms of activation function, if you mean sort of theoretically, can you like pick a particular activation function to make things easy? Then yes, you can. That's the value. There's a vast literature on theoretical properties of the value and all sorts of showing that networks with the value can do all sorts of things. But I think, at least for me personally, it's the general case.
You suggest that ReLU might be actually identifiable as an optimized choice over some family.
Oh, I see. That I don't know. So what I simply meant is that the value is like, it's easily understood. It has friendly algebraic properties so that it's easy to analyze. I don't know that it's optimal in any sense. This, to be honest, like from an empirical point of view, like you want to train a neural network to do a good job, this is a completely open question. People really have no idea what makes a good activation function. And there's plenty of proposals, most of them saying, let's take the value and tweak it a little bit to try and do something better. But I don't think there's any good theory sort of cohesively describing what's going on.
Thanks for that. Thanks for a fantastic talk.
Thank you.
Well, while we see if there's any more questions, I have perhaps a basic question which sort of goes back to the original universal approximation theorem. Is what is it about polynomial activation functions that make them a separate case?
Okay, so if we've got this picture here, the problem about polynomial activation functions is that if you imagine each one of those blue neurons is just computing some polynomial of degree n of its inputs, well, it's the same polynomial for each time, So each neuron is a degree n polynomial, and you add up a bunch of degree n polynomials, and you're still only a degree n polynomial. So you're limited by the things you can approximate up to degree n. So in particular, you can't get any general continuous function. You can't go to higher degrees.
Okay.
Does that make sense?
Yeah, no, that does make sense.
Yeah.
Okay, that's interesting. Oh, and my other quick question was about, you talked a little bit about sort of sparsity, so that your depth, your deeper network is actually can be quite sparse. But how would you deal with things that aren't sort of straightforwardly feed forward, things like convolutional layers and things like that?
So the result that we're stating here is really just about feed forward, which again is this sort of like over-analyzed theoretical case that isn't necessarily what's used in practice. And so for convolutional networks, I think there is a result out there. I think it's one of Peterson's papers, which says that any result on feed-forward networks can be extended to convolutional ones in certain ways. So those at least I think you can handle. But like generally, I agree, right? You know, that we need to be considering slightly more realistic neural networks as well.
Brilliant. Okay. Thank you very much for your talk again. We're a few minutes early.